Hi, I'm Ajay, and I'll be your pactor for probability. Probability probably is one of those topics in mathematics that is easy, and at the same time, the foundations can get very complicated. It is very important topic, especially related to applying mathematical knowledge towards better prediction models. As usual, we'll be using the why effect, that is, what, why, when, where, who, and how to complete our journey of probability. In this chapter, we will cover the theoretical probability, also called classical probability. The experimental or empirical probability is not covered in this chapter. Let's start with some facts. The assumption is that you have a good understanding about these facts. I hope you have played with coins and understand what is heads and tails. The coin considered for experiment is considered to be unbiased. That is, it is symmetrical and has no reason to come down more often on one side or the other. Again, the assumption is that you have played with the dice and understand the use of the same. The dice considered for experiment is also considered to be unbiased. Similarly, it has no reason to show a specific number more often than any other. It is also assumed that you have played with cards and understand the color and order, that is 1, 2, 3, 2 kings. For clarity, a deck of playing cards has 52 cards divided into 4 suits of 13 cards each. Spades, hearts, diamonds, and clubs. Spades and clubs are black and hearts and diamonds are red in color. Each card suit has 13 cards and are marked as ace, king, queen, jack, 10, 9, 8, 7, 6, 5, 4, 3, 2, as is shown here. King, queen, and jack are called face cards. So let's start our journey of learning probability. Obviously, the first question is, what is probability? Probably is the first word that comes to mind when we think of probability. Probability is the measure of the likelihood that an event will occur or how likely is a proposition true. Probability is quantified as a number between 0 and 1, where 0 indicates impossibility and 1 indicates certainty. The higher the probability of an event, the more certain we are that event will occur. But let's start with some fundamentals about probability. So, what is a trial? An experiment is any procedure that can be infinitely repeated and has a well-defined set of possible outcomes. Performing an experiment is known as a trial. Example, tossing a coin. The possible outcomes are heads or tails, assuming you are not tossing in a sand and the coin will not land on an hedge. So fundamentally, if a coin is tossed, the chances are known, so tossing a coin is a trial. Similarly, rolling a dice, the possible outcomes are 1, 2, 3, 4, 5, or 6. So what is an event? In continuation to probability, an event is an outcome or defined collection of outcomes of a random experiment. In a trial of tossing the coin, giving heads or tails is an event, or in a trial of rolling a dice, giving 1, 2, 3, 4, 5, or 6 is an event. Probability majorly can be classified into 3 possible ways. Number 1, experimental or empirical probability. Number 2, theoretical or classical probability. And number 3, axiomatic probability. Experimental probability is an estimate of the likelihood of a certain outcome based on repeated experiments or collected data. It is basically on what actually happened. I always say experimental probability is the probability of something happening in future based on the past experiments. For example, if on flipping a coin 10 times, 7 times heads came and the rest 3 times tails came. So based on these experiments, we can say that the experimental probability is 7 by 10 of coming heads and 3 by 10 for tails. Theoretical probability or classical probability is probability that is determined on the basis of reasoning. The probability is calculated by utilizing the knowledge of certain situation and not actually carrying out an experiment. For me, theoretical probability defines the probability of something happening in future based on logical options possible out of the various other possible options. Axiomatic probability is based on set of axioms that apply to all types of probability. This is covered in advanced classes, so we'll not be covering it in this chapter. In this course, we will concentrate on theoretical probability. I would again repeat that in this course, we will concentrate on theoretical probability. In this course further, all experiments have equally likely outcomes. Wait a second, but what is equally likely outcomes? So let's take an example. If we take an unbiased coin, assuming the coin is not landing on the sand as suggested earlier, the possible outcomes are heads or tails. The chances of the coin landing as heads or tails is equal. So an unbiased coin has equal chances of getting heads or tails. So an unbiased coin has equally likely outcomes. Similarly, let's take a dice, rather an unbiased dice. The possible outcomes are 1, 2, 3, 4, 5, or 6. The chances of any number coming on the face of the dice is equal. So, an unbiased dice has equal chances of getting any number, that is 1 by 6. So, an unbiased dice has equally likely outcomes. Let's take bag of balls. In this bag of balls, we have 4 blue balls and 1 white ball. The chances of picking a blue ball versus a white ball is not equal, obviously. As the chances are not equal, this bag of ball having 4 blue and 1 white ball does not have equally likely outcomes. Let's take it further with a detailed example. As a bag of ball also can show equally likely outcomes. Let's take an example. Anjali has a bag that has 4 balls, 1 each of color red, green, yellow, and blue. Are the outcomes of each ball equally likely? The total number of balls that we have is 4. Red, 1, green, 1, yellow, 1, blue, 1. The chances that we pick a red, green, yellow, or blue color ball are the same out of 4. So the outcomes of each ball are equally likely at the present time. Now, another ball of orange color is added. Let's assume that. So are the outcomes of each ball still equally likely? Total number of balls is 5. Now we have 1 red, 1 green, 1 yellow, 1 blue, and 1 orange. A new ball of orange color is added, and that color is not there. So now when we pick any ball, the outcomes of each ball are still equal, 1 out of 5, as there are 5 balls in the bag. Now another ball of red color is added. Let's assume that. Are the outcomes of each ball still equally likely? The total number of balls is equal to 6. Red 2, green 1, yellow 1, blue 1, and orange 1. As we already had a red ball in the bag, so the chances of picking a red ball will be more than the rest of the balls, which means that now the outcomes of picking a random ball from the bag are not equally likely. It is important to read the question and scan if the question mentions or implies equally likely outcomes. Now, I hope with this example, you understood what is equally likely outcomes. Let's talk about what is theoretical probability again. Theoretical probability, also called classical probability, can be considered the theory behind probability. It is not required to conduct the experiment. Instead, the possibilities of event happening is used to calculate probability. So fundamentally, the trial actually never happened. It is based only on the possible favorable outcomes from all the possible outcomes. it is very important to acknowledge that the theoretical probability of an event E is written as P parenthesis E. Again, this is important thing to note, as this is how mathematicians talk about probability. P of E is called probability of the event E. So PE is equal to the number of outcomes favorable to E divided by number of all possible outcomes of the experiment. If you are able to really absorb this formula, you just need to understand it in a very simpler detail. Number of outcomes that favor the event E, that is happening of the event E, divided by the total number of all possible outcomes of the experiment. Here, we assume that the outcomes of the experiment are equally likely. So, P of E is always greater than or equal to 0 and is always equal to or less than 1. Let's take a simple example of an unbiased coin. Find the probability of getting tails when tossing the coin. Also find the probability of getting a heads. The question always assumes unbiased coin or dice. Take this as a pointer that if nothing is mentioned in the question of probability, it is always assuming that it is an unbiased coin or dice. Let's talk about the solution. In the experiment of tossing an unbiased coin, possible outcomes are tails, which is marked as T, or heads, which is marked as H. Say T be the event of getting tails. The number of outcomes favorable to T is 1. So the probability of T, that is number of outcomes favorable to T, divided by the number of possible outcomes becomes 1 by 2. Say H be the event of getting heads. The number of outcomes favorable to H is 1. So probability of H, that is probability that heads is turning up, is equal to number of outcomes favorable to H divided by the number of all possible outcomes, that is whether heads or tails. So that also is equal to 1 by 2. So both probability of event T, that is tails, and probability of event heads is equal to 1 by 2. Both probability of T and probability of H are elementary events, as their outcomes are only 1. This is important time to again register a terminology, elementary event. An event having only one outcome of an experiment is called an elementary event. Let's take another example of an unbiased dice. Let's throw a dice once. What is the probability of getting a number greater than 3? The second part to this question is, what is the probability of getting a number less than 3? And the third part to this question is, what is the probability of getting exactly 3? Let E be the event of getting a number greater than 3. The number of possible outcomes is equal to 6, as we know, that is 1, 2, 3, 4, 5, and 6. The favorable outcomes of event E are either 4, 5, or 6, which implies that the favorable outcomes to the event E is 3. So the probability of the event E, that is getting a number greater than 3, is equal to 3 divided by 6, which is equal to 1 by 2. So now we look at the second part of the question. Let F be the event that is getting a number less than 3. Number of possible outcomes again is the same, which is equal to 6. Outcomes favorable to the event F are only 2. That is, if the dice shows 1 or 2. So the probability F, that is probability of the event getting a number less than 3, is equal to 2 divided by 6, which is equal to 1 by 3. And finally, the third part of the question, let G be the event of getting exactly 3. Again, number of possible outcomes still remains the same, that is equal to 6. Outcomes favorable to the event G is 1. So the probability G, that is probability of getting exactly 3, is equal to 1 by 6. Here also, just as a reminder, we can see that only event G is elementary event and E and F are not elementary event, as their outcome is not only 1. It is important to note in the above examples that probability of tails plus probability of heads is equal to 1. It is also important to see that the probability of getting a number in a dice greater than 3 plus the probability of getting the numbers less than 3 plus the probability of getting the number exactly as 3 is also equal to 1. We can finally say that sum of the probabilities of all events of an experiment is 1. In addition, if we think probability of tails, that is P of t, plus probability of not having t is also equal to 1. Same is true for all events. So probability of not having a tails is referred to as Pt bar. The event probability of not of t is called the complement of the event t. I again repeat, the event P not of t, that is not tails, is called the complement of the event t. The probability of an event which is impossible to occur is 0 and called impossible event. The probability of an event which is sure or certain to occur is 1 and called sure event or certain event. Finally, taking another example, and this time a card example. One card is drawn from a well-shuffled deck of 52 cards. Calculate the probability that the card will be a king or it will not be a king. The description of a deck of cards was mentioned earlier in the assumptions, and we have a well-shuffled deck to make sure equally likely outcomes of drawing one card from the deck. Number of kings in a deck is equal to 4. So let K be the event the card is a king. The number of favorable outcomes to have a king, that is K, is equal to 4. The number of total outcomes of drawing any card is equal to 52. That is the total number of cards of the deck. So the probability of K, that is probability of drawing a card as king, is equal to 4 divided by 52, which is equal to 1 by 13. For the event not a king, we assign the event as n. So probability of n, that is not a king, so probability of not a king is equal to 48 divided by 52, which is equal to 12 by 13. We can also see that P of n is equal to P of k bar, which is equal to 1 minus P of k, which is equal to 1 minus 1 by 13, which again is equal to 12 by 13. That is just a verification that the sum of the probability of an event plus the complement of the event is equal to 1. Let's take another card example. All face cards only, the jack, queen, king from a deck of 52 cards are taken, then are shuffled with their face down. One card is then picked at random. The first part of the question is, what is the probability that the card is the queen? And the second part is, if the queen is drawn and put aside, what is the probability that the second card picked is also a queen? Description of the deck of cards was already mentioned, and we have a well-shuffled deck to make sure equally likely outcomes of drawing one card from the deck. In a deck, we have 12 face cards, 4 jacks, 4 queens, and 4 kings. So let PQ be the event of picking queen out of 12 cards. The number of favorable outcomes is equal to 4, and the number of total outcomes is 12. That is number of total face cards. So the probability of Q, that is probability of drawing a queen, is equal to 4 divided by 12, which is equal to 1 by 3. Now, let's approach the second part of the question. One queen is already taken and kept aside. So now there are 4 jacks, 3 queens, and 4 kings remaining. So let PR be the event of picking queen after a queen has already been picked and kept aside. The number of favorable outcomes now is equal to 3, as there are only 3 queens left. And the total number of outcomes is 11, because now the queen had been kept aside and that queen cannot be taken. So now the probability R, that is the probability of an event R of picking a queen after a queen has already been picked and kept aside, is equal to 3 divided by 11. Just an out-of-the-box question to trigger your mind. Why study theoretical probability? Not all experiments can be conducted or controlled. Tossing a coin or rolling a dice can be conducted again and controlled too. But imagine experiment of launching a satellite. In order to compute the probability of its failure cannot be conducted again or be controlled. Similarly, an experiment to measure the probability of a multi-storied building getting destroyed in an earthquake cannot be conducted or controlled. There are many cases where measuring theoretical probability gives a good indication of the chances of something happening or not happening. Let's discuss few real-life examples that can give us a better understanding of use of theoretical probability. There are 50 students in class 10th of a school. Out of all students, 20 are girls and 30 are boys. Class prefect has to be selected from all students. The class teacher writes all the names of the students and the numbers in chits and puts them in a bag and pulls out a random chit. What is the probability the student is number 1, a girl, and number 2, a boy? Let's look at the solution. There are 50 students. Only one name card has to be chosen. The number of possible outcome is 50. The number of girls that become the favorable outcomes for the girls is 20. So the probability of the event of girls is equal to 20 divided by 50, which is equal to 2 by 5. The number of outcomes favorable for boys is equal to 30. So the probability of selecting a boy in the chit is equal to 30 divided by 50, which is equal to 3 by 5. We can also see that the probability of boys is equal to 1 minus probability of the girls, which is equal to 1 minus 2 by 5, which again turns up to be 3 by 5. This is kind of a verification. Let's take another example. One card is drawn from a well-shuffled deck of 52 cards. Find the probability of getting a queen of red color, a face card, a red face card, the jack of hearts, a spade, a 10-faced card. I know these are 6 possible parts of a question, but let's tackle it one by one. So the solution, chances of drawing a card are equally likely in a well-shuffled deck. Total number of outcomes possible is equal to 52. So the first part of the question is a queen of red color. There are 2 red queens. So the probability of queen of red color is equal to 2 divided by 52, which is equal to 1 by 26. The second part of the question, a face card. That is a king, queen, or a jack are face cards. There are 12 face cards in a deck. So the probability of pulling out a face card is equal to 12 divided by 52, which is equal to 3 divided by 13. The third part of the question is a red face card. Out of the 12 face cards, half are red. So there are 6 possible outcomes. P of red face card is equal to 6 divided by 52, which is equal to 3 divided by 26. The fourth part is jack of hearts. Only one possible outcome is possible as we have specified that it is a jack and it is of hearts. So the probability of jack of hearts is equal to 1 divided by 52. A spade. 13 cards are spades. So 13 outcomes are possible. So the probability of drawing a spade is equal to 13 divided by 52, which is equal to 1 by 4. And the last part of the question, what is the possibility of drawing a 10? So there are 4 tens, so the possible outcomes is equal to 4. So the probability of drawing a 10-face card is equal to 4 divided by 52, which is equal to 1 by 13. I know this was pretty quick, but now you see a pattern developing in you. Probability as an abstract concept is generally combined with other concepts of many subjects, especially mathematics to solve decent problems. Let's take examples of some simple mathematical concepts where probability, if combined to get information, is very useful. A box contains 100 discs which are numbered from 1 to 100. If one disc is drawn at random from the box, find the probability that it bears a 2-digit number, a perfect square, which is the second part of the question, and the third part of the question is a number divisible by 5. Now here, we need to have a good understanding about numbers also. So the total number of discs is equal to 100. This question requires basic knowledge of numbers, as I said earlier. This can be used to calculate favorable outcomes. Solving the first part of the question, all numbers from 10 to 99 are 2 digits, and which is equal to 90. So the outcomes which are favorable are equal to 90. To the event of selecting the probability of 2-digit numbers is 90 divided by 100, which is equal to 0.9. Let's look at the second part of the question. The perfect square numbers are 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. So the outcomes that are favorable is equal to 10. So the probability that we are drawing a disk which is a perfect square is equal to 10 by 100, which is equal to 0.1. The third part of the question asks about the numbers which are divisible by 5. So in 100, we see that the numbers divisible by 5 are 5, 10, 15, 20, 25, and so on. Just keep on adding 5 till 100. And we all know that it's just a multiplication of 5. So the outcomes favorable is equal to 20. So the probability that we are drawing a disk which is a number that is divisible by 5 is equal to 20 divided by 100, which is equal to 0.2. This is how probability is applied to general concepts. Let's take another example where probability is combined with general common sense. A box contains 12 balls, out of which X are black. If one ball is drawn at random from the box, what is the probability that it will be black ball? If 6 more black balls are put in the box, the probability of drawing a black ball is now doubled of what it was before. Now we have to find X. Let's say the total number of balls is equal to 12. Number of black balls is equal to X. So the probability of drawing one black ball is equal to X by 12. So let's mark this as P of A, that is probability of the event A. Now 6 more black balls are added. The total number of balls now is equal to 12 plus 6, which is equal to 18. And the total number of black balls now is equal to X plus 6. So the probability of drawing a black ball after addition of 6 black balls is equal to X plus 6 divided by 18, which is equal to, let's say, probability of B. Now, what is given in the question is that the probability of B is 2 times the probability of A. Putting the things in equation, we have X plus 6 divided by 18 is equal to 2X divided by 12, which implies that X plus 6 is equal to 18 into 2 divided by 12 into X, which implies that X plus 6 is equal to 3X and X is equal to 3. This brings us to the conclusion of the chapter of probability, where we covered theoretical probability. Probability is considered one of the complex topics, but we have just uncovered the tip of the iceberg. We were able to impact your learning about probability. We had a lot of fun creating this course for you, and as per the calculated probability, you liked it, or you would not be listening till the end. Hope you liked our presentation. Enjoy the challenges.